Imagine a wall of invisible air, thousands of miles wide, suddenly halting the planet's entire weather system in its tracks. This atmospheric phenomenon, often called a blocking pattern or weather plug, can trap extreme conditions over regions for weeks. These powerful atmospheric blocks are colossal high-pressure systems that become stubbornly stationary, defying the usual west-to-east flow. They act like giant corks, preventing normal weather patterns from moving through, creating prolonged periods of unusual conditions. Understanding these plugs helps us comprehend why some regions suffer extended heat waves, while others endure endless rain. Such blocks can entirely reroute the jet stream, the fast-moving river of air high above us that steers most weather systems. When the jet stream encounters a strong block, it splits and flows around it, leaving the area beneath the block undisturbed. This trapped air mass then dominates local weather, often leading to record-breaking temperatures or relentless precipitation. Scientists observe that these blocking patterns typically form when large-scale atmospheric waves become unusually amplified and stationary. Specifically, disturbances in the upper atmosphere, sometimes linked to planetary Rossby waves, can initiate this process. These waves, like ripples in a pond, naturally propagate across the globe, but sometimes they get stuck in place. The key ingredient is a persistent ridge of high pressure, extending vertically through the troposphere, becoming incredibly robust. This strong high-pressure system then diverts the polar jet stream, forcing it to take a much longer, more circuitous route. Think of it like a boulder in a river, causing the water to flow around it, creating stagnant pools upstream and downstream. One common configuration is the omega block, named for its resemblance to the Greek letter omega, with two low-pressure systems flanking a high. This setup creates a stable, unmoving high-pressure center, effectively plugging the atmospheric flow for an extended duration. Another type, the Rex block, features a high-pressure system sitting directly north of a low-pressure system, stacked vertically. This vertical alignment further enhances stability, making the system incredibly resistant to being dislodged by other weather forces. But that's not the strangest part about these atmospheric anomalies and their persistent nature. The energy within these blocking patterns can actually self-reinforce, making them incredibly difficult for other systems to break apart. They essentially create their own favorable conditions, maintaining their position through a complex interplay of pressure and temperature. Wait until you hear how these seemingly stable systems can suddenly collapse, leading to dramatic shifts in weather. When a block finally weakens, the pent-up weather systems, previously diverted, can rush in, causing rapid and intense changes. Imagine a dam breaking. The flood of air rushes to fill the void, often bringing storms or sudden temperature swings. The exact mechanisms causing a block to dissipate are still areas of active research, involving intricate atmospheric dynamics. Sometimes, a strong upper-level trough can erode the ridge, while other times, internal atmospheric instabilities lead to its breakdown. The persistence of these atmospheric plugs has profound, far-reaching consequences for human populations and natural ecosystems alike. Extended periods of drought, for instance, devastate agriculture and increase the risk of widespread wildfires across vast landscapes. Conversely, a stationary block can funnel moisture into one region for weeks, triggering catastrophic flooding and landslides. Many historic heat waves, like those experienced in Europe and North America, directly correlate with the presence of stubborn blocking patterns. These extreme temperatures strain power grids, cause heat-related illnesses, and significantly impact vital infrastructure. Similarly, prolonged cold snaps, often associated with Arctic air trapped by blocks, can severely damage crops and disrupt transportation. The economic toll from these weather plugs can reach billions of dollars, affecting industries from farming to tourism and energy sectors. Understanding these blocking patterns is therefore crucial for improving long-range weather forecasting and preparing communities. Better predictions allow for proactive measures, like water conservation during droughts or evacuation planning for anticipated floods. Scientists utilize sophisticated climate models and satellite data to monitor the formation and evolution of these atmospheric plugs. This continuous monitoring helps identify potential blocking events early, providing valuable lead time for public safety warnings. We are constantly learning more about how these powerful phenomena interact with a changing global climate system. The future of atmospheric science relies heavily on unraveling the full complexity of these persistent and impactful weather makers. These invisible atmospheric walls are truly among the most powerful and enigmatic forces shaping our planet's climate. Grasping their behavior is key to anticipating and adapting to the extreme weather events they so frequently unleash. The intricate dance of global atmospheric forces continuously sculpts our weather, sometimes with surprising and enduring results. These atmospheric plugs represent a fascinating frontier in our ongoing quest to understand Earth's dynamic weather systems. If you found this exploration of atmospheric blocking fascinating, subscribe for more incredible stories like this one. Want more mind-blowing facts about our planet's complex mechanisms? Hit subscribe and join our journey of discovery. You can also let me know in the comments what other weather phenomena intrigue you most.